Hello everyone, my name is Jacob Peroni, and I'm here to present my project on noisy class labels on deep neural networks. The outline for the presentation is going to be as follows. I'm going to first talk about the issues of noisy labels on deep neural networks. I'm then going to talk about the current approaches and solutions that have been applied to remedy those issues. I'm then going to offer a critique of the approaches and solutions, and then finally we're going to end with a conclusion and future work that can be done in this area. So deep neural networks can suffer from poor performance when noisy labels are in the training data. Noisy labels are wrongly assigned classes in supervised learning. Many training data are labeled by either non-experts or by automated systems, which give higher levels of noise, especially when you consider the massive size of the data that is needed to be used for training a deep neural network. So acquiring high quality annotated data is very costly and time consuming, which leads to most deep models being trained on data with a large amount of noise. This in turn leads to deep models overfitting on the noisy labels. The success of deep neural networks is largely dependent on carefully labeled datasets, as clean datasets have been proven to yield better results. Even though deep neural networks can fit a whole training dataset, it can still have poor generalizability on test data. Generalization capability with noisy labels is thus really a key challenge for deep neural networks. Now there's also different types of label noise. Most existing algorithms are based around instance-independent label noise. This noise assumes that the corruption process is conditionally independent of data features when the true label is known. Here the noise can be considered symmetric, where the label can be flipped at an equal probability into other labels, or it can also be asymmetric, where the true label can be flipped into a particular label. There's also pair noise, which is when a true label is flipped into only one certain label, which then creates a pair between the two. There's also instance-dependent label noise, which is more realistic noise modeling. It assumes that the corruption probability is dependent on the data features and the class labels. More studies do need to be done into this type of noise as it has complex modeling. So the first solution I'm going to talk about is called O2UNet. This solution is a novel noisy label detection approach for deep neural networks without the human annotations. So this novel approach does not require a specially designed noise robust loss function, which makes it really easy to implement. It only requires adjusting the hyperparameters of the network to transfer from overfitting to underfitting cyclically. It can identify noisy data by calculating and ranking the normalized average loss of every sample. As the higher the loss of the sample, the greater the probability of it being noisy. So this approach does reduce annotation cost, which is a really big advantage. The intuition behind this approach is that noisy samples are memorized at the late stages of the deep neural network training as hard samples. They're trained from easy to hard, sort of similar to curriculum training or learning, which we're going to talk about as another approach later on. So once memorized, these losses would decrease really fast. So this solution applies multiple rounds of the status transfer, which is the over to underfitting, cyclically by changing the learning rate to a cyclical learning rate. The noisy labels can then be identified by the statistics of their losses during this cyclical training. And as previously mentioned, a larger average loss would be a higher probability of it being a mislabeled sample. There is an assumption of this solution in that the gradient computation is dominated by clean samples when the network is underfitting, as the proportion and distribution of noisy labels would have a greater effect on label noise detection. Cyclical training works via a large learning rate, which as it converges on a minimum, so nearly overfitting, the large learning rate makes the network jump out of the minimum, and then the network then becomes underfitting. So during the cyclical training, the loss of every sample is recorded. Once the whole of the training is finished, the average of normalized losses of every sample is then computed and ranked descendingly. Then the top K% is removed, where K is chosen by prior knowledge of the dataset. Applying multiple rounds of cyclical training reduces the statistical bias of sample losses. Now we're going to talk about the robust architecture approach. Having a robust architecture for deep neural network is an approach that can combat noisy datasets. This can come from developing either a noise adaptation layer on top of a deep neural network to learn the label transitions, or by creating a dedicated architecture that supports diverse label noise. The noise adaptation layer finds the noise transition matrix, which is the label transition pattern that is discovered from the training data. This layer is usually put on top of the softmax layer, and these architectures can generalize well by modifying the deep neural network output to be based on the estimated label transition probability. To note, this layer should be removed when test data is to be predicted, as it's really only a training use only layer. Dedicated architectures look to increase reliability of estimating the label transition probability so that more complex realistic label noise can be handled. Compared to the noise adaptation layer, dedicated architectures are more robust to different types of label noise. Directly training noise-robust models on unclean data introduces regularization to reduce the effect of overfitting on noisy data. By avoiding overfitting in model training, regularization techniques such as data augmentation, weight decay, dropout, and batch normalization improve the model's robustness to label noise. Weight decay and dropout are explicit regularization, which have a huge performance gain if they can be optimally tuned. They have model-dependent hyperparameters or need a deeper architecture because of the reduced capacity. Data augmentation and batch normalization are implicit forms of regularization, which gives the effect of stochasticity. This regularization improves generalization capability without the reduced representational capacity that's seen in explicit regularization. There are also no model-dependent hyperparameters in implicit regularization because this is applied to the training data only. Creating a robust loss function is another approach that can be applied to combat noisy labels in deep neural networks. This approach is supported well theoretically, but only performs well in the simplest of cases, such as learning on a small number of classes. Also to note that when modifying the loss function, the training time for convergence is also increased. Loss adjustment is an approach that looks to reduce the negative impact of the noisy labels by adjusting the loss of all training examples before updating the deep neural network. Loss adjustment has 4 methods that are generally used. They are loss correction, loss reweighting, label refurbishment, and meta-learning. Loss correction estimates the noise transition matrix to correct the forward or backward loss. Loss reweighting gives different importance to each example for a weighted schema. Label refurbishment adjusts the loss based on a refurbished label, which comes from a combination of noisy and predicted labels. Meta-learning infers the most optimal rule for loss adjustment. Meta-learning looks to improve noise robustness by applying a concept of learning at a higher level rather than conventional learning. This is also called learning to learn. This then becomes a data agnostic and a noise agnostic rule, which can be used for more better practical use. Sample selection is an approach that selects true labeled examples from noisy datasets, which allows the deep neural network to update only on clean examples. This approach typically uses multiple deep neural networks or runs multiple training rounds, such as what you heard in the O2U net solution. Loss correction can also be applied with this approach to benefit from falsely labeled examples. Multi-network learning is a derivative of sample selection with two highly used schemes, collaborative learning and co-training. In the case of collaborative learning, the sample selection process is determined by the mentor network, while in co-training, it is determined by the peer network. The deep neural networks are maintained simultaneously, and they only update the examples where there is a disagreement between the two neural networks. With collaborative learning, the mentor network provides the other network with examples that likely have correct labels, while the co-training network will take a few small loss examples and feed them to the peer network for more training. Multi-round learning iteratively refines the selected set of clean examples by repeating the training rounds. The set keeps improving the more rounds that are done. So detecting and cleansing noisy labels before training can be done. This approach is really simple. You just first detect the noisy labels, and then you either remove them from the training set or you feed them to the model after the clean samples. This reduces the negative impact that the noisy labels have on the model. Practical usage in the industry for this include yielding clean datasets, which can then be used for other tasks via transfer learning without considering the impact of the noisy labels. A dataset is allowed to be verified and annotated multiple times to guarantee its cleanness. It can also have active learning done to it after the noisy label detection to reduce the human annotations. Curriculum learning can be used to build more robust models, as estimating probabilities of noisy labels can develop such a curriculum and extend the applicability of noise cleansing models. Curriculum learning is the same intuition as the novel approach that was seen in the OTUNet solution. The curriculum is designed to rank the difficulty of training samples, and easy samples are trained first to introduce robustness to the model. This can be seen as a function of sample losses. So curriculum learning follows how humans learn, starting from the most basic examples first, and then going up to the advanced concepts later, as opposed to having examples just randomly presented to the model. This allows for a faster conversion speed of the training process. In addition to just plain curriculum learning, there are also other methods, including self-paced learning, balanced curriculum, self-paced curriculum learning, progressive curriculum learning, teacher-student curriculum learning, and implicit curriculum learning. Presented on this slide is the pros and cons of all the approaches and solutions discussed so far. I'm now going to talk about each individual one and their critique of it. So starting with OTUNet, it's a solid solution to noisy labels on deep neural networks. It's very straightforward and it lowers the cost and complexity. OTUNet gives a solution that has high applicability because of just how simple it is to implement. This solution can be applied to the diverse demands of practical use. This solution has the least amount of drawbacks that I've seen, as it does not need any extra design functions to achieve really great performance. The robust architecture approach suffers from an inability to identify false labeled examples, as all examples are treated equally. This leads to a large estimation error when only noisy training data is used, or if a dataset with a high noise rate is used. Dedicated architectures may be able to tackle more types of label noise, but it cannot be extended to other architectures as easily. Regularization techniques do not completely overcome the overfitting problem by themselves. While the regularization techniques mentioned do well on moderately noisy data, they alone are not sufficient enough to improve performance. And when they're used on noise-heavy datasets, they achieve poor generalization. There is an advantage to using these regularization techniques, and that is the flexibility that they provide, as they only require simple modifications. Implicit regularization has a slowed down convergence on training because of the extended feature/label space that it has. The loss adjustment approach looks to make the optimization process robust to label noise. The update rule is adjusted in the middle of training to minimize the negative impact of the label noise. Since the loss adjustment goes through every example, full exploration of the training data can be done. Now, a con to this approach is that the error incurred from false correction is accumulated, and this is especially seen when the number of classes is large or when the number of noisy examples is large. Now, loss correction robustness is dependent on how precise the transition matrix is estimated. Prior knowledge is often required, such as having a clean validation data to get an accurate transition matrix. Loss reweighting looks to apply smaller weights to noisy labels and larger weights to true labels, but this approach needs to manually pre-specify the weighting function and its hyperparameters. This is difficult to do in practice, as there's a lot of variation of weighting schemes that rely on noise and training data. Label refurbishment can be effective at preventing overfitting to false labels. This is because the noisy labels are explicitly replaced with other expected clean labels, or a combination of both. This works well at refurbishing noisy labels in data where classes are not confusing, and can do so with very high precision. But the opposite scenario is also true, in that the deep neural network can overfit wrongly refurbished labels. Meta-learning allows the trained network to learn the update rule and easily adapt to different types of data and label noise, but it needs unbiased, clean validation data, which may not always be readily available. The co-training approach of multi-network learning reduces the confirmation bias. That's favoring examples selected at the beginning of training. With this, having many learning parameters makes the learning pipeline really inefficient, while multi-round learning expands the clean set with more clean examples by increasing the rounds. The computation cost for training increases at a linear rate for the number of rounds. Noise robustness is improved when combined with other approaches, but again, as stated, the computational cost will then also increase. Also, the hyperparameters that these techniques of sample selection use can render deep neural networks susceptible to changes in data or noise type. Curriculum learning offers a structured and organized training set to learn on. A notable model that's used in practical use is MentorNet, and that encompasses the curriculum learning methodology. Curriculum learning may provide useful supervision to help a student network overcome corrupted labels. However, there are some limitations to the curriculum learning methodology, such as existing curriculums are predefined and they remain static throughout training. This in turn leads to the network, the mentor, ignoring feedback from the student network. To conclude, each approach/solution discussed has shown promise in tackling the hindrance that noisy labels have on deep neural networks. Of the approaches and solutions presented, OTUNet I think offers the best solution, as it gives a simple and novel algorithm for addressing noisy labels. This in turn lowers the complexity and the cost, as there's no need for human annotators to clean the data. Curriculum learning also has high promise for the future of deep learning. Having that structure for training has improved performance on a variety of problems already. As of now, deep learning is computationally expensive and requires multiple high-end GPUs to operate at an acceptable level, which just ends up leading to a higher cost for users. Deep neural networks have already solved many problems and made many advances in a lot of fields, but more research and um, more approaches being tested could further evolve the field. Deep neural networks rely on having a clean dataset to achieve maximum performance, but for real-world application, there will always be noise that affects the data, whether it comes from being mislabeled by humans, or just missing the labels altogether, or even having it changed by an attacker. The noisy labels will always be there. The research into deep neural networks is still growing and will continue to evolve as our understanding of how they work and as more approaches and solutions are tested and revised. Possibly finding a cheaper way to get quality data could facilitate deep neural networks, as that would alleviate one of the biggest entry costs and training factors, as deep neural networks really heavily rely on clean data to perform well. Future work could include studying how using multiple approaches together could affect the robustness of the deep neural networks, particularly if it negates some drawbacks that the individual approaches have. Future work in curriculum learning could involve applying a dynamic curriculum that changes based on the student network feedback. This would give more use for complicated learning procedures and can have them be more accurately modeled. These are the references used for this presentation as well as in the associated project. This concludes my presentation on noisy class labels on deep neural networks. Thank you and have a great day.